Hey everybody, welcome to today's webinar. Go ahead and get started here in just a few minutes. We'll let some more people funnel in. All right, well, just out of respect for everybody's time, we can go ahead and get started. So welcome to today's webinar. It is titled Modeling Compressible Fluids and Power Generation. So thank you again for taking the time and joining us today. My name is Lake Lund, and I'm a Business Development Manager here at Commonwealth. Today's session is designed for professionals across the power engineering industry. So whether you're just beginning your career or looking to take the next step in your advancement, today's session is going to be a perfect and ideal fit for you. So a little bit about Commonwealth. So we are an employee-owned firm that is located and headquartered out of Jackson, Michigan, which is, it's for some of you guys that aren't familiar, it's just a little bit outside of Detroit. So I'm sure that everybody up in Jackson is pretty excited for the Tigers and Guardians game later today. We have about 250 employees and have 7 office locations across the United States. We are a soup to nuts engineering and consulting firm with over 37 years of experience in the power industry. We provide expert engineering and consulting services for the energy market. Our expertise encompasses power delivery, power generation, system studies, and consulting. And if you want to learn more about us, please check out our newly revamped website at cai-engr.com. So today's session will make you eligible for a PDH certificate. You can email us at marketing@cai-engr.com to receive the certificate. At the very end of the presentation, I'll post the email so you guys can take a picture, make sure you get that jotted down. And so we want today's session to be as engaging as possible. So please submit your questions in the Q&A section by clicking the Q&A icon in the top of your screen. And then we'll get to those after the presentation has concluded. And again, feel free to ask as many questions as you would like. We'll have some time at the end to get to those. If nobody asks any questions, then I have to ask them. And nobody wants my questions as a BD person. So today's webinar will be recorded, and we will be sure to post that on our YouTube channel. There is a QR code at the bottom right hand of your screen. Please go ahead and scan that if you guys would like to be subscribed to our YouTube channel. We post all of our webinars and other presentations that we do across the nation on our YouTube page. Our next webinar will be in late October, and we'll have some more details to follow on that. We'll be posting those on our LinkedIn page and also sending out email campaigns so you guys are aware of that. So I'm going to post a poll right now in the chat here. The poll is, have you heard of AFT Arrow prior to this presentation? And I'll get that going here in just one second. All right, and then without further ado, I will go ahead and introduce our speaker today. Okay, and you all should see that poll pop up. Feel free to answer that while I introduce our speaker. So with all that said, it's my pleasure to introduce Aaron Cruzel. He is a rising force in the world of power generation engineering. He's based at Commonwealth Associates in Michigan. Aaron brings a sharp blend of technical expertise and field-tested experience to the table. He's a graduate of Michigan Technical University and has a degree in mechanical engineering. He is a licensed PE in the state of Michigan. Over the past 5 years, Aaron has built a strong track record in both design and commissioning, with a particular focus on the complexities of combined cycle power plants. His work bridges the gap between precision engineering and real-world performance. And today, we're lucky to hear from someone who's shaping the future of energy.
Alrighty, well, thank you, Lake. Appreciate that very nice introduction. So yeah, I'm Aaron Cruzel. I'll be doing the presentation, and let's get into it. Alrighty, so Basically, I want to start with a safety moment just to keep all our minds on safety. It's something we should all strive for and always wanting no accidents, making sure that we're creating safe systems for our clientele and for the people that operate it. So moving on to that, I wanted to go into the complexities of pressure testing. So a major part of construction is testing in some way the pipe that we design. So making sure that the rigidity, the structure, everything is going to hold at a lower pressure by testing it at a higher pressure. So doing this, there's two methods, hydrostatic and pneumatic. Hydrostatic uses a non-compressible fluid and usually about 1.5, I think it's exactly 1.5 times the design pressure according to ASME standards. So with this, you have a small exclusion zone. Usually water is the media used, and it's a pretty standard process. It's the typically recommended method by ASME. So the alternative to this is pneumatic. It uses a compressible fluid like air or nitrogen or some inert gas that actually tests the same piping but with a compressible fluid. So this is done at 1.2 to 1.5 times the design pressure and is generally not specified, and it's not recommended by ASME unless recommended by the owner and requested by the owner. So that is who the onus is on for choosing this. Generally not recommended because it has a large exclusion zone and for a few other reasons I'll get into. So what happens when these go wrong? With hydrostatic, if this testing fails, generally it's a pinhole leak or something small, a gash in the side of the pipe that expands and a small squirt of water comes out. And due to the compressible and non-compressible natures of air versus water, with water, the amount of compression that happens, the actual density of the water doesn't change significantly, while with a pneumatic system, the density does change significantly when you press more and more and more air into a cylinder, a vessel, a pipe, whatever it's being tested. So what happens when they fail? This is a aftermath of a site in Shanghai. This was a testing of LNG facility. They were doing a pneumatic test, and there was a catastrophic failure. I don't want to get too much in the details, but essentially a major piece of equipment failed while testing at over almost 2,000 psi. The impact to the site was massive. It was a 6-month delay. It pushed back millions of dollars of revenue that they were going to receive once the plant started. But more importantly is the human factor. Someone lost their life as well as 15 people being injured, and it was a major catastrophe. And the one thing that stood out to me was the distance. Someone was killed almost a quarter mile away from where the explosion happened. They were unrelated to the site, not unrelated to the site. They were a worker at the site, but not working. They were off shift. They were not doing the testing, but a piece of scaffolding material came, impaled them, and killed them. So it's a very large impact this testing can have, and at such high pressure, the explosive and fragmentation force of this compressed system is going to it can cause a major catastrophe if it fails. Going back, that's why if ASME doesn't recommend it unless it's designed, it's not that it's inherently unsafe, it's that when it does fail, it has a massive catastrophic effect. So just being aware that if you sign off on a pneumatic testing or there's debate on it, this is something to be considered. Not that it should never be used, but that it should be used sparingly and with constraint and caution. So that is my safety moment. So yeah, moving on to the core of the presentation, I'm going to switch screens. Oh, I shared the wrong screen. Sorry, guys. There we go. All right. So this is AFT Arrow. It's a very useful software in power generation as well as any industrial piping situations. Very useful tool. So what does it do? It essentially takes a model, and it's a mathematical model of what you make, and then it runs extrapolations and iterations of the actual flow through the pipe, the media going through, and it does all these internal calculations to spit out a very accurate result depending on what you put into it. Again, garbage in, garbage out, but with the right inputs, you can create a very complex system and solve it essentially, and make sure that you are designing it correctly. So let's get into it. It's pretty straightforward. I'm going to make a very basic system here and then show you a more complex model that you might have seen on my previous screen share. So getting started, we're going to start with a flow. So let's say you have a air system. This is what I'm designing to. So I've selected this fluid of air, and I have an end user that requires, let's say, 100 SCFM, so standard cubic feet per minute. So I'm going to choose that SCFM, toss in an arbitrary number of, actually I think we'll do 300. And we'll say it's coming out at ambient temperature. We're assuming 70 F off of the receiver. From there, we want to have an end pressure. So let's say the end user, a control valve, a airdrop, anything that would use a pneumatic system and control system for air, it's going to require a certain amount of pressure. So let's say our pressure that we're desiring is in PSIG, and we're looking for 100 PSIG. And let's just assume there's no temperature drop, 70 F for our outlet. Okay. Now what do? We have to connect the two. So we're going to add some pipe. That's kind of my bread and butter. So easy peasy for me. And there we go. Perfect. System's done. So now we're going to have to add some constraints. Elevation in pneumatic systems is important, but less important than for a water system or a compressible fluid or non-compressible fluid situation. So we're just going to say 0 feet of elevation change between the two. Not saying that there's, it's at sea level. It's just saying between the 2 points, there's no pressure or no elevation change. For our pipe itself, I think we're going to say 2 inches to start, and it's about 100 feet of piping that we're going to have. So 2 inches of basic steel. You can change this to any material that might be existing in a current plant or plan for the future plant, as well as the schedule. You can change that to whatever, but for what we're doing, this is a pretty standard pipe for a air system. So moving on, I'm going to press OK, check that everything is working the way we're intending. Everything is green checked, so good to go. We're going to run it. So the output for AFT Arrow has a couple of different very useful features. First and foremost being the tabular output. It's very detailed with what it gives you. But personally, I find it a little bit hard to just look at this and inherently know what the system's like. So I prefer the visual report for just a baseline understanding. So here I have some preset conditions that show my outputs. Based on this, we're getting a mass flow of 0.38 pounds per second. We have a pressure out of 115 psi, which is 100 psig, and the same output pressure. So we're getting almost no loss through this actual pipe because we're going at a slow enough velocity where it's not slowing itself down by losing energy to the pipe itself. That being said, our standard tries to, we have a Commonwealth standard to pinpoint the velocity. So for our system of air, for a distribution header, we're trying to shoot between 30 feet per second and 50 feet per second. So we're a little bit low. So that means we can squeeze down our pipe and more accurately, that more accurately fits the system. So we can squeeze down theoretically to 1.5 inch pipe and input in, test, get our output. And look at that, it's between our 30 and 50 feet per second. That being said, what we're not accounting for in this current very basic model is pipe loss. So stuff like a flange or a bend or a valve, anything that obstructs the easy path of a cylindrical pipe. So to do that, we're going to go back to our workspace and account for those losses. So what we can do is actually go into the pipe itself, and this is really useful for anything in a existing system or a system that's being designed. So it has both versatility in retrofits as well as greenfield, brownfield, whatever type of construction that is new construction. So it has both facets because you can model old systems and add to new systems, or you can make an entirely new model for a new system. So very useful there. So going in, we're going to go to our our fittings and losses, and then add some equipment and stuff that's going to be on this actual pipeline. So we'll add some bends. There's a smooth flange. We can say, this bends up, over, down, over, let's say five bends. And then we can add some more. So let's say there's some valves. We'll say a ball valve on either side to isolate. So simple enough. We add 2 ball valves. And then let's add a flange and account for how it's being connected up. So from where it starts to where it ends, we're adding another flange, typical 150 class. Okay, that gives us a total K value for how much loss is going to be coming from these pieces of equipment. This is something that if you're a mechanical engineer, you've probably calculated in your fluid dynamics class at some point, I think way back when. But with Arrow, it's a lot quicker. So we can just real quickly, you saw me add these, and now they are accounted for in this pipe system. So we run it, and there should be a little bit of a pressure drop now. So you can see now to account for the 115 psi A that we're getting at the end, we have to up our input pressure, and now it's showing 117. So what does that mean? Let's say your compressor is running and you are putting out 100 psi or 102 psi now, you're dropping down that 2 psi. Let's say there was more tumultuous of a path. That's going to drop it down another 5 psi, 10 psi, and then theoretically, if there's a lower limit to what the end user can receive, then you start losing efficiency. You might even lose function of the equipment. So accounting for that pressure loss is very important. So let's add some more equipment to this. We have a few options on this side. We have control valves, we have pressure relief valves, we have orifices, we have heat exchangers, compressors, spray nozzles, a whole kit and caboodle. We have all the options for what a power plant or any industrial system that uses pipe would be utilizing. And if it's not in the actual software, if it's some proprietary piece of equipment that has very specific tuning, you can still put that in. You can still have a junction that mimics said equipment with the losses accounted for, any heat exchange accounted for. So it's a very useful software where if it doesn't immediately have what you need, you can make it have what you need. You can add it in yourself. So it's a really useful piece of equipment, piece of software that it's not necessarily the most intuitive. I've had a bit of experience with this program myself, and I'm still learning. I've spent over 5 years learning on this program, and I still find new things. So it's quite fun for me. So let's add this piece of equipment. I'll stop rambling. So let's add a heat exchanger. I'm just going to insert this into the pipe. And then I'm going to say it's pretty close to the end. So let's say 10 feet at the end. So you can see by this ampersand, that's the equipment that still has the valves and the bends and the equipment, the flanges that we added. So it's still accounted for, but now it's just on this piece of pipe. So if you wanted to change some of those, you could move them over, but here nor there. So getting into the heat exchanger itself, we're going to put a arbitrary number. I'm going to say a factor of 5 for the K factor. And then for the actual thermal data, I'm going to say it is a constant downstream temperature. I want to have a downstream temperature that is 70 degrees. I'm going to assume that, let's say coming off the compressor, this is some piece of pipe. It's actually going to be too hot. So we want the end product to be 70 degrees, but it's coming at us at 40. So what we can do is modify this, have a thermal output of 70 degrees F, and by adding this heat exchanger in, we can get the end result, fingers crossed, of a heat exchanger that gives us 70 F out when it's coming in at 140. So really useful. It's a lot of stuff like this where you're adjusting and correcting and adding it in, but sometimes it works out perfectly the first try. So now let's look at it. We have this visual model, and it's very useful for making and creating, but then for the actual brass tacks, the output, this is where you want to be in the tables. So we are able to actually pull a lot of information for sizing and for other things. So for the heat exchanger summary, you can see in this top left corner, I can actually know the mass flow, the differential pressure going through this heat exchanger, the temperature increase, but most importantly, the heat rate in. So this is kind of your heater information. So this is something you can bring to a vendor and say, hey, I need this piece of heater or this cooling equipment, in this case, I need something that can take this many kilowatts or BTUs per second or BTUs per hour away from the system. And with that, you can go to a supplier and you can get these procurements started. It's a very quick process. Instead of doing a hand calc, I can very quickly have a estimate using this software. You don't have to wait for a long multi-page calc to figure out how much flow is going through, how much heat is being lost. It's a very quick process for if you want to have quick results, you can get a very instantaneous proposal ready. Sorry, headphone cut out there. On the other side of things, if you want something more precise and less quick, you still have the ability to have a more detailed program. You don't have to do something as simple as a straight line with a heat exchanger and a pressure output. You can have something more complex like this. So this is a more complex model that I've been working on. It's for a client of ours. Not going to get into the proprietary information for confidentiality, but essentially it's a natural gas supply for a data center. And we have multiple units running off of one natural gas supply. We have a pressure in, we have flow rates out for multiple users. Each generator, each CT combustion turbine is going to have a supply of a certain amount of gas that you need to supply it at a certain temperature. We have to meet those requirements. In addition, we have to account for any future users on the site, so accounting for that pipe flow, as well as any user in the HVAC for the warehouse for heating, making sure personnel are comfortable with the temperatures. So based on that, you get a lot more complex results, and the amount that goes into the system increases. You have that finer detail, and you can still use it for the proposal, the procurement, and getting like high level equipment specs. But you also can fine tune everything. So each piece of equipment here can be adjusted to have the right amount of bends, flanges, valving. Everything can be accounted for in the software once you have that information. So it's an evolving software. As the project continues and it evolves, the software and the model can evolve. So you're not just stuck at a basic understanding. You can complexify and make it more detailed. For example, we have added compressors and heat exchangers to account for what we need to supply to the end user, and we've been able to send those out to our procurement specialists, and our procurement team can get started on this stuff, and as well as like electrical. So with our results, if you see them, we get some compressor results as well. So in addition to like sizing heaters, you can size other equipment like compressors or I guess I'm blanking, but heat exchangers, compressors, any piece of equipment that's large enough, dew point heaters or knockout drums, stuff like that. And by having that information for the electrical equipment side of things, you can tell your electrical team, I need this many horsepower motors, and you can get them that ballpark early enough so they can start their procurement of all their electrical stuff that I'm not going to even talk to. So based on this, you get a more complex visual result. You have the flows coming out. And then in addition to what we're seeing for, with the last one, the velocity, we can also account for pressure loss. So accounting for how much is actually dropping in the system is lost to the pipe. And we can make sure that all end users are going to get a consistent or at least high enough pressure at the end result. So that's kind of the twofold piece of how we design our systems, is both having the velocity to meet the sound requirements as well as the degradation of the pipe, but then the pressure drop to make sure that the end user is actually getting what they need. So pretty cool with a little more complex of a software. Really, I don't know. I find it very cool. It's cool how much you can put into a software and how it can evolve with a project. Speaking of, with our compressor sizing, let's say you size your compressors, you go out for procurement, you get your pump curves or your compressor curves. something that's super useful is you can directly put these into the software using this compressor curve data. And by doing so, you can verify what conditions you're going to get. So you've already bought the equipment, making sure that, yes, you can do a sanity check, verify that everything is operating as it should. Or if you have a plant that's already existing, you can put in the compressor data from the existing plant. So let's say you had this entire system. This was already an existing plant. So you have, I think, 17 here, 17 CTs operating. But let's say you want to add more. We have some future units accounted for. How much more compression do we add with 3 compressors that are already sized, already, fit to a curve? But let's add another, size it, and then you can actually know how much horsepower you need for this compressor. It adds a really useful ability to have retrofit accuracy. So being accurate with your retrofits, making sure everything, one, fits, for sizing, but then making sure the pipe can actually handle it. So let's say you add another compressor. Sure, you have the theoretical ability and it has the rated ability to shoot out, a couple thousand SCFM of natural gas, but what if the pipe can't handle it? So being able to model that allows you to have visibility and very, very clear understanding of what your system is able to do. Alrighty. I'm going to go back to the presentation. Actually, you know what? Just while I have these softwares up, does anyone have any questions about AFT Arrow? Not sure if everyone's muted. We can wait on that. For the time being, I'll get back to the presentation.
Yeah, I'm not seeing any right now, but I'm sure there will be afterwards.
Okay. Go. Alrighty. That showing up for everyone, the presentation we had up earlier?
Good to go.
Alrighty. I did see one question about a database of piping material. Is that correct?
Yes.
Okay. So to answer that, yes, there is a large database. Let me share back. So in the actual AFT software itself, when you're selecting these pipes, you have a plethora of different materials. So it can be copper piping, HDPE, stainless, regular steel, ANSI. But then you also have the ability to do any custom piping. So you can, again, adjust to a user specified. You can specify what type of pipe it's being used. You can dictate the size. Generally, cylindrical piping is pretty typical, but then you can choose the inner diameter. So there's some pieces of like HDPE piping doesn't have the largest selection. So if you had to account for that for like a very large HDPE size, pipe size, you could account for that and add that in. I think that hopefully that answers your question. You can also adjust the absolute roughness of the pipe. So if you it has some pretty, I think they're decent presets, but if you know that this piping is a little bit rougher than what the model is showing for friction loss, you can account for that. Another cool feature of the piping is the actual design factor. Something that we can do is account for a 1.1 factor of design just for aging. So as this pipe ages, it's going to get pitting, it's going to have forms of corrosion in the pipe usually. You can account for the added friction and the added pressure loss or energy loss as it's going through by accounting for that in the design factor. Cool. Hopefully that answers your question. And I think we'll get to the presentation now. Okay, so what does this look like from a client side? The end result is going to be a P&ID deliverable. We're wanting to deliver something that can be constructed to isometrics, but most prime example is P&IDs, and this is what goes to the client. Based on what we've modeled, we can size the equipment, we can actually, size the piping correctly and then input it into our P&IDs, which then in turn can go to our general arrangements. It's generally how we actually make the model is pulling pipe lengths and estimations from the actual GAs itself, and then coming back and adding the actual line sizes, equipment sizes, all that jazz. So this is more the end result of what comes up after completing and finishing up the actual model. So why does this matter at all? Like why would we use this expensive software? It's a very expensive piece of software that costs a lot each year, and it takes a lot to train on it. Why would we do this instead of a hand calc? Why couldn't we just estimate the size of the pipe? It's a pretty simple calc to figure out velocity. Same with pressure loss. It's not a superly overly complex calculation. Like, why couldn't we do this by hand? And ultimately, you could, but the amount of iterations and versions that you can make of this, it's going to take a lot of man hours and mental effort and time to maintain and update as each step of the project comes up. You're going to get new information and redoing that calculation over and over, and truly without as much accuracy, because you're not accounting for, again, those bends, those pressure losses, the flanges. You have to calculate that all, and generally it's not done. It's just done by adding a margin onto the actual end result. You add a certain amount of margin to the flow or to the pressure and the velocity, and you end up with generally not necessarily oversized pipe, but less optimally sized pipe. So for example, a major point, if you're at 4 inches or 6 inches, that is a huge price point over the course of the amount of piping you're having. So for example, if you're going from 1,000 feet of 4-inch pipe to 1,000 feet of 6-inch pipe, you're nearly doubling the cost. And it gets additive. I believe for a simple or a combined cycle 300 megawatt power plant, it's upwards of 100,000 feet of pipe. Like it can have massive amounts of pipe, and that cost adds up. And that's not just the piping itself, it's the valving that associates with it. It's the different pieces of equipment that you're driving this compressible fluid through. If you have an undersized pipe, the equipment is going to have to work a lot harder to flow through that, and there's going to be a degradation to the pipe as it flows through. The velocities are going to be higher, so you're going to get more wear and tear on the system. So there's a plethora of reasons, and it really comes down to the accuracy of the main model, which is how you size everything, but then on top of that, the complexity and the ability to create different cases. Something that I didn't show in Arrow is the clone feature, the child feature, basically creating a base version and then subsequent versions of the different cases that your plant would experience, that the system would experience. So accounting for that high flow state or that low flow state, you're able to do it all in the software, and then using hand calcs and backing it up and making sure you're not just relying on the software, you can 100% validate the system will work in every situation. And doing that by hand it's prohibitive by time. You don't have the time to do that. But with the software, with AFT, you're able to. So it gives you a lot more ability to pinpoint precision, sharpen your pencils, get the most accurate answer, and at the end of the day, that saves money. If you oversize the system, sure, it's going to be a cost loss. It could cost a lot more if you oversize. But the alternative, if you undersize, you got to tear out that system. You have equipment failing prematurely. You have warranty issues. It's a lot worse to size it incorrectly. Obviously, that's not a new statement. That's not something that everyone didn't already know, but it's easy to see the numbers and understand the pipe costs a lot more to make and to install than it is to spend a little bit of time engineering, making sure it's done right in the first place. So Moving on, Lake, I am ready for Q&A.
Perfect. Thanks, Aaron. That was a very good presentation. So it looks like Kyra asked a question. So what are some of the challenges you face with the software and how have you found solutions?
Ooh, challenges in the software. I would say with any modeling program, there's a learning curve. As I said, I've worked for over 5 years using this program, and I still find ways for it to trick me. There's always going to be, minute details that, if you don't have experience in the program, it makes a lot of sense once you're operating it. Like, okay, this pressure can't drop negatively. You can't add pressure through a control valve. It only loses pressure. So stuff like that, accounting for system clunkiness. But overall, I think the most challenging part is it's not. How do I put this? It's making sure everything is accurate. There's so many fine details in a model that a small adjustment could have cascading effects, and it's inaccurate. So I think the hardest part and the most challenging part of the software is the attention to detail, making sure that what you're putting in, garbage in, garbage out, good quality in, good quality out, making sure that everything is accurate for how you're modeling it. So I think that's one of the harder parts of the software.
Hey, thank you. Very good answer. So next question, this is one that I'm asking, and if anybody has any questions at all, feel free to put them in the Q&A section, and we'll be sure to get to those in 1 second. In the meantime, how do you balance cost and operational efficiency when modeling compressible fluids for new power generation projects?
That's a tough one. It's a coordination effort between us and our procurement team, our estimating folks. Just coordinating with them, as well as I think just being in the industry, you gain a understanding of what stuff costs. I think just having the experience and I guess the knowledge that we have at Commonwealth, being able to apply that direct knowledge of, okay, is this equipment, like how expensive is this equipment? How expensive is this piping? It is a balancing act. There's no doubt about it, but I think it's less it's more about the actual knowledge gained and the expertise than like a physical, like, oh, this is a set number. It's not like it's a calculation per se. It's more, I don't want to say by feel or by vibe. It's not. It's about having a basis and understanding with our estimating team how much something costs and whether it's worth it or not. In general, it's not done through AFT. Like it's helpful in the process. It's a piece of the puzzle, but it's not like the main driving factor of efficiency, per se.
Very good. So it's a mixture of collaboration internally and externally with our partners as well as expertise.
Yeah. Yep.
Fantastic. So to kind of piggyback off of that question, without getting into details on the client or the exact project, can you think of a real world example where modeling led to a significant design change or an operational improvement in a combined cycle plant?
Um, for combined cycle, gosh, I don't have a specific example for AFT Arrow, but I do have one for AFT Fathom, which is the non-compressible fluid side of AFT. It was a cooled water system, circ water system, and we were designing it, and our pressures were coming out the way we were expecting them. But there was a cost savings that we incurred because we realized at the pressure we were operating at and the kind of the flow rate that we were and the temperatures we could change from a carbon steel piping to a HDPE, a PERT, a polyethylene raised temperature piece of pipe, which is significant cost reduction. It basically halves the pricing of the pipe itself because it's a polyethylene instead of a carbon steel, which you have to weld. You have to have all these different methods of transportation. It just the additive cost of changing from a steel to a polyethylene mixture pipe it just saved a bunch of money. So we were able to do that because we modeled it in Arrow. It allowed us to understand that, okay, even with the increased thickness of the actual pipe, if you don't know, HDPE has much thicker walls at the higher end of the pipe size. Even with that, we were meeting our velocities, we were meeting our pressure drops. So we were able to actually switch without any major impacts to the system.
Fantastic. No, that's exactly the response I was looking for. Thank you, Aaron. And it looks like that's all the questions. Let me refresh really fast. Okay, I do have one from William Turkovich actually. So, Aaron, from your perspective, which would you think takes more man hours to complete a QC process for projects, by hand calc or software based?
Can you repeat that? Like for QC, is in like is the
Quality
software?
assurance. Yep.
Yeah, sorry. I guess from my perspective, with how we do these models, these are not standalone models. These are always backed up by hand calcs. These are always verified using our internal QC. Um, so I guess I'm struggling to answer it because it's not a case where it's one or the other. It's not one is, it's always the model is the kind of the basis. It's not the entirety of the calc. So I guess from a QC perspective, it's not like it's used to quality check. It's more that it is the one half of the hand calc calculation. So when I say hand calc, I mean like an exclusive back a napkin calculation, like something that's more high level and doesn't have the precision of using a modeling software. It's exclusively using one. I find that the quality comes out much higher when you use them in tandem. So I guess it's not a great answer. I'm sorry, but it's kind of hard because they're used so integrally. Integrally, yeah, they're used together.
Fantastic. Okay. Well, I think that'll wrap up the Q&A. Appreciate the questions, everybody. Thank you.
Yeah. One thing that I forgot to mention earlier is the diversity of materials that can be used, media, I should say, in the actual piping software. So I was just showing two basic systems, a compressed air system and a compressed gas system. Both very common in the power industry, both very prevalent, but that's not it's all limited to. There's steam, so any steam system can be modeled. That's super beneficial for combined cycle power plants, which I have a bit of experience with, as well as nitrogen systems. Anything that is a compressible fluid is in the software. And I saw that comment come up. Yes, it has a massive database of ASME steam tables, of proprietary AFT, I guess not proprietary, but their own database of materials and media, I should say, as well as a ability to input any combination of fluids that you want. So for example, I had a natural gas system. I got the chemical breakdown of how much methane, how much propane, how much X hydrocarbons are in each. And I was able to input each one individually by mass percentage or by mole percentage. And you can have a very accurate fluid, which gives you a very accurate model. So there's a large amount of different fluids that can be used, as well as anything that you could think of if there's like a proprietary refrigerant or any type of fluid that is not in the software, it can be added. So that's a nice piece of the puzzle.
Fantastic. Go to the final slide here, Aaron, if you would. All right, so just some final notes here. So again, if you guys would like to claim your PDH credit, please email marketing@cai-angr. If you fail to write that down, you can always email myself as well. And our next webinar, I did get some information on that. So it's going to be October 29th at noon to 1 Eastern time. And it's going to be, the title is Soil Measurement and Modeling, the Foundation of Good Grounding. And this is a part of our Power System Studies webinar series that we've been putting on for a little while now. So we'll be sure to send out some information on that on LinkedIn. So feel free to check our LinkedIn out, and I'll have a QR code for you to follow us on the next page. And again, the webinar recording will be posted on YouTube. So feel free to share with your colleagues. If you guys have any questions, you can rewatch it. The next slide, Aaron. Go. All right, and that'll be it. So thank you, everybody. Again, please follow us on LinkedIn, and thank you so much for taking the time. Everybody on our team here at Commonwealth really appreciates your support and you guys taking the time to watch this presentation. Thank you so much, and have a great rest of your Thursday.